So let me just retreat for the purpose of the record. Let me retreat what I said. I said, first of all, the mode, when I talk about mode of vibration, it simply mean the pattern of motion in which all the parts of the system moves sinusoidally with the same frequency and with a fixed phase relation. So basically, that is it. So the pattern in which a vibration takes place, or a part of the systems move sinusoidally. And this is kind of what you mean by a mode of vibration. Now, we are saying that every stationary wave occurs between two boundaries. And there are two forms of the boundaries we are talking about. We have the free and we have the fixed boundaries. And so when you look at a typical wave, right from what you've been studying, when you look at a typical wave, where's my two this thing? I'm coming. When you look at a typical wave like this, the other day we studied the modes of the wave. When you have something like this, the other day we studied that the size of this are the nodes, and here this is the antinode. Do you remember? You remember we studied this?
Yeah, you spoke about them. I did not draw this one.
Ah, okay. So I use this drawing. I use this drawing. You remember I use this drawing? Yeah,
Yes, sir.
it's the same thing. So it's just more or less like losing it like this. It's the same thing. So that is it. So when you have something like this, we have the nodes and we have the antinode. When you have something like this the node here is one, the antinode is one, and the nodes are two. Now, the nodes normally constitute that of what you call it. There are two main forms of boundaries: the free and the fixed boundaries, and a stationary wave. That's now the antinodes, which is normally the point of maximum oscillations. So the antinodes are normally the point of maximum oscillation. So that's the maximum oscillation. You get it? That's the point of, that's the antinode, and they are normally a point at which the vibrating particle have maximum amplitude. And the notes are normally at the point of zero vibration. So you realize that normally here is the maximum vibration. When it gets here, it gets to zero, then it starts again. So the notes are normally at zero, what do you call it, zero vibrations. Then the antinodes are normally at maximum vibrations or maximum amplitude. You get it? And so that is where the antinodes are, and the notes are normally at zero vibration or zero amplitude. Now, normally the notes occur at a fixed boundary. You realize that this one occurs at a fixed boundary. It occurs at a fixed boundary, as a fixed boundary. Then this one occurs at a free boundary. So you realize that here there's movement. So the antinode normally occur at, what do you call it? Uh, the antinode occur at. Hey, my phone has started full again. The antinode occurs at. The antinode normally occurs at a free boundary. So that is it. And that will help us understand what you call the modes of vibration well. That will help us to understand the modes of vibration you're talking about. So we are saying that the nodes and the antinodes occur also with the boundaries. So that is it. So they occur with the boundaries. And normally the nodes occur at the fixed boundary, and the antinodes normally occur at the free boundaries. So basically that is it. So the free boundaries, the fixed boundaries, and so on and so forth. So the nodes occur at, I told you that we have two modes of, what do you call it, two forms of boundaries in every stationary wave. That is the free boundary and the fixed boundary. And we are seeing that the antinodes normally occur, which is the maximum oscillation, normally occur at the free boundaries. Then the nodes occur at the fixed boundaries. So fixed. I hope you get it. We are doing sound waves. Now, stationary waves occur in stringed instruments. Stationary waves occur in string instruments. So stationary wave occurs in string instruments, stringed. It occurs in stringed instruments. Occurs in string instruments. I'm just looking at some instruments that stationary wave occur. And when we talk of string, we are talking about this thing. It also occurs in pipe instruments, in windpipe instruments, open tubes or pipes. So we can call them open tube, or pipe or pipes in which the boundaries are free. Open tube or pipe in which the boundaries are free. Boundaries are free. It also occurs in what do you call it? It also occurs in a closed tubes in which the boundaries are fixed. Occurs in closed tubes or pipes, or occurs in closed tubes or pipes with one side open, or pipes with in which pipes in which one boundary is fixed and the other one is free, and another free. So we have string instrument where the boundaries are. So what do you call it? The stationary waves normally occur in string instrument in which the boundaries are two fixed ones. So normally the boundaries are two fixed ones, like the guitar. The boundaries are two fixed ones. When we get there, we're going to explain. Then we're also going to work on the open tubes or the pipes in which the two boundaries are free. And we can also look at the closed, what do you call it? The closed tubes or pipes in which one boundary is fixed and the other is free. These are some instruments, some of the trumpets and so on and so forth. It looks like the pipe. You get it? Some of these things. So I'm going to look at them. I'm going to look at their mode of vibration and how it occurs. Now, the modes of vibration occur in stationary, this what do you call it? That occur in stationary wave normally depends on the types of boundaries involved. So the modes of vibration, that means the movements or the way, what do you call it? All parts of what do you call it, the vibration, the system moves sinusoidally normally depends on what do you call it, the modes of the vibration that occur in the stationary wave depends on the boundaries involved. So the modes of vibration that normally occur in the stationary wave normally depends on the types of boundaries involved, just as I've already explained. Now, the foremost mode is the fundamental. The first mode we are going to consider is the fundamental mode. And each instrument has the first fundamental mode. Now, when there's been an increment, then we go to the what they call it, the first overtone, and the second one we go to the second overtone, and so on and so forth, the third and the rest, based on the movement of the wave. So the first movement is what we call the fundamental, what do you call it, the fundamental mode, or the first mode is what we call the fundamental mode. Yeah, Ruben, talk to me.
Say, please, what's the overtone?
So that was how in this case I'm coming. Uh, so I'll explain to you, so don't worry. So the first mode we are going to consider is the fundamental, what do you call it? The first one I'm going to consider is the uh, fundamental mode, which is the longest wavelength possible in the instrument. So the first mode we are going to talk about is the fundamental mode, which is normally the longest wavelength possible in the instrument. Now, the longest wavelength which occurs when the vibration is in the first tone, overtone, is what we are going to look at. Then we are also going to look at the second overtone, and that's it. Now, the overtone has a frequency, definitely, and is an integral multiple of the first frequency, which I'm going to explain when we start doing the mathematics. In other words, we call it harmonic. When you do music, you get to understand what harmonics are and so on and so forth. My phone is full then, but I'm coming. So when we say an overtone, it's normally a term that is generally applied to any higher frequency standing wave. You get it? So we realize that the first frequency we are talking about, when we talk about vibration, we are talking about frequency. Now the first frequency we are talking about is what we call the fundamental. Now when we increase the frequency, the second upgrade of the frequency is what we call the higher frequency, what we call the overtone. You get it? And so it will be like an improvement on the second one. Then we can go on and get what we call the second overtones and so on and so forth. So overtone is a term what is generally applied to any higher frequency standing wave. That is basically that is it. And a series of it is what we call harmonics. A series of it is what we call the harmonics. So while the term harmonic is reserved for those cases in which the frequency of the overtones are integral, so a series of it is what we call the harmonics. So I hope you get the overtone now. Higher frequency standing wave.
Yes, sir.
Good. So higher frequency standing wave. So that is it. So basically it's a frequency. Now the fundamental one is what we call the first one is what we call the fundamental mode. And the second one is what we call, or the next one is the overtone, the first overtone, and we go to the second overtone, and so on and so forth. And all these things we use mathematics. We are going to relate them in terms of their mathematics and so on and so forth, and we'll just be good to go. That is basically it, and we'll be good to go. So now let's first consider fundamental mode of vibration in a string instrument. So now let's look out for the mode of vibration in a string instrument. We are going to look out for the fundamental mode of vibration and a string instrument. We can use that to get the second overtone and so on and so forth. Normally, the fundamental is what is the most important thing. Now, so the fundamental mode of a vibration in string instruments. So we are going to consider the fundamental mode of vibration. Fundamental mode of vibration. String instrument. So let's first consider the first what do you call it? In a string instrument, the fundamental vibration has two notes. So it will be like something like this. So in the first this, its fundamental vibration has two notes. So the two notes will be this and this, and definitely we'll have, and the two notes will constitute the fixed ends. I told you that in a string instrument, it has boundaries which are two fixed ones. So that is it. So it has two fixed boundaries. So that is it. This and this. Then it has an antinode. There's the antinode. So that is it. Now from here, the length of this from here to here is what we call the length. So in a string instrument, the fundamental vibration has two nodes and the fixed ends and an antinode between it. Now this means that the distance from the end to the subsequent end is what we call the L. So the distance between the two nodes is what we call the L. Is what we denote as L. And the L is equal to, well, this L is equal to the wavelength all over 2. You realize that when I draw something like this, when we're doing that of a sinusoidal wave, we said when you have something like this, from here to here is just half of this thing, half of what you call it, a wavelength. Now, so this diagram is more or less like me drawing something like this. Me just picking this part. So this part from here to here is just half of a wavelength. I hope you know that. So the length
Yes,
is
sir.
equal to half of the wavelength. That's the length or the distance between the two nodes is what's equal to half the wavelength. And so that is this all over this. So we can say that wavelength can also be equal to twice of what they call the length. That's mathematically. Please, you understand? But oh, oh man. So that is it. Now, uh, but we know that the speed of the wave passing in a string. You know, when we talk about vibrations of a string here, we are talking about the vibration, the first vibration of the string instrument. The string instrument. Oh, my instrument is wrong. You just rectify it. When we talk about the first fundamental distance, the speed of the wave passing in the string will be equal to, you know, the speed is equal to the frequency of the wave times the wavelength. So when I have a guitar and I strum the guitar, the speed of it is what they are talking about, the frequency. That's, you know what frequency is, times the wavelength. The wavelength, that means the length of the wave. So we're going to have this. Where now here, F is a fundamental frequency. Here we are talking about the fundamental. So F here is the fundamental frequency. So looking at this from this mathematics, we can just make some deductions here. We can substitute this one into the work. So we can get V is equal to 2LF. Do you agree with me? Where F is a fundamental frequency. Now, in this case,
Yes.
in a stretched string, fundamental frequency can be equal to the speed of that is in a string, or the speed of the wave passing in a string, all over what do you call it, 2L, where L is the distance between the two nodes. Please, do you understand? So that can be a
Yes.
good. Now, the speed of a wave in a string is also related to tension. You know, anytime we talk about a string, we talk about the tension of the string. So the speed of the wave in a string is normally related to the tension in a string. So the speed of the wave in a string is also related to the tension in a string. So we can say that it's related to the tension in the string and the mass per unit length of the string. So the speed of the wave in a string is also related to the tension in a string. And you know that there's tension in a string. Mhm. That's how it's able to stretch and is able to listen. So there's tension in a string. So the speed of the wave in a string is related to the tension in a string and the mass per unit length. So when you have a guitar, before you can strum it to get a good sound, you have to tighten inside. Now when you tighten it, you create that tension in it. So if you over tighten it, you realize that it will get torn and it will tear. The string will tear because it has exceeded its elasticity. It has exceeded its elasticity. So that is it. So we are saying that then the speed is also proportional. No, is equal to this. So we can relate with this. T, it is related to T all over M, where M is the tension and M is what you call the mass per unit length of the string. So that is it. Now looking at this, we know that V is also equal to 2LF. So we can say that 2LF is equal to root of T all over M. Now, when we talk about variation, I'm talking about frequency. So frequency will be equal to frequency can be equal to 1 all over 2 L root the tension in the string all over the mass. That is it. So it follows that the frequency, the first what we call the fundamental mode of vibration in a string instrument, and that the frequency, the fundamental frequency is equal to 1 all over 2L times the root of the tension in the string all over the mass. Are you getting it? So we've been able to use this. So the first mode of a string instrument, it has two notes and there's an antinode. Now having two notes and there's an antinode, the distance between the two notes we denote that by L. But looking at the sinusoidal curve or the sinusoidal wave, this thing form, you realize that from here to here is just half of a wavelength. The full wavelength is from here to here. So that is what we are going to get. And immediately we move from here. So this one is the first fundamental. Now we move from when this one comes to add, then it becomes the first overtone. And when another one comes to add, then we get the second overtone. I hope you get it now. So that's the first frequency, the first oscillation. Now the second one, then we are getting at a first overtone. And so on and so forth. Please, are you getting it now?
Yes, sir.
Good. So you can bear with me that the first overtone with this L will now become L will be equal to what? L will be equal to lambda instead of 2 lambda over 2. L will be equal to lambda. That is when L is equal to this. When we do it, when we get there, we will do it so you understand it better. So that is it. So the L is equal to this, and we're able to get the wavelength. Now we equated or we found the relation between the speed of a wave with respect to that of the frequency of it and the wavelength, and we're able to arrive at this. And we made a wavelength, what do you call it, stand out. We had V all over 2L. Then now we said that the speed of a wave in a string is also related to the tension of it. The tension of it and what do you call it? The mass per unit length. So the mass of the distance, we look at it, then we made V the subject by bringing in 2LF. And we made F the subject and we're able to get this. I hope you get it now. When you're done writing, you let me know.
Yes, sir.
When you're done writing, you let me know. So I'm hoping we can finish all the modes today. When we finish, I have to talk about a mode of open tubes and pipes. Then we do the closed tubes. Then we are done. And maybe next time we can do Doppler effects. Then we are done with sound waves. Let's just read it. You can go and read. I'm waiting for if you are done writing, let me know. Yeah?
I'm done.
Good. So that is now. This therefore means that the frequency of a stretched string is inversely proportional to the length. So looking at this, you can say that the frequency of a stretched string is inversely proportional to the length. It's inversely proportional to its length. So here we are going to, you can see the length of the string and so on and so forth. So the frequency of a stretched string is inversely proportional to its length. So we can see that we can take some notes. Let me just erase some part of it. So we can say that frequency, looking at this formula, I can say that frequency is inversely proportional to the length. Inversely proportional to the length. So we have this. Inversely proportional to the length. So the frequency of a stretched string is inversely proportional to its length. So that's the first thing we can do. So since it's inversely proportional to its length, we can get F1. When we have the length 1 and the length 2, we can get F1, L1 is equal to F2, L2. So you can just keep this formula anytime you are using it. So the pitch of the note is inversely proportional to the length of the string for the same string under the same tension. Now we can also get the second deduction that the frequency of the vibrating string is directly proportional to the square root of the tension in a string. Yeah, Ruben, talk to me.
So you say it is inversely proportional. So how come is F1 L1 is equal to
So
F2?
this is gotten from this formula. It's gotten from F is equal to inversely proportional. So for instance, if we take frequency 1 is equal to 1 all over L, 1 sorry, 1 all over L. There is mathematics. 1 all over L. Length 1, we can multiply this. When we multiply, we are going to get F1, L1. Haven't you seen it? And that is should be equal to when you take frequency 2 and L2. That is the same. That's what we just meant. So it is gotten from. So this is gotten from what do you call it? F is proportional to the length, inversely proportional to the length. That basically it. So you can just keep it for, as a formula or something. Now, the second note we should also take that the frequency of the vibrating string is directly proportional to the square root of the tension in the string. So you can see that the frequency here is also directly proportional to the square root of the tension here. Or F is directly proportional to the square root of the tension here in a string. For the same string, the pitch of the note increases with increase in tension applied between its ends for the same length. So that is it. So we can also consider it being directly proportional to the tension. So when you increase the tension, you can increase the frequency. So frequency is also directly proportional to the square root of the tension. The square root of the tension. Now when you have this, it's equal to you can have this. When we take away this, we can bring in kt or k root t or something. Or you can, when k is 1, we can just get f is equal to root t. Now this can also, so anytime you have f1, if you have f1 and t1, what do you call it, t1, we can get f1 all over f2, unlike this one will be equal to t1 all over t2, all over t2. And this is also the same as this formula. It's just derived from this formula. We have the frequency 1 and frequency 2. This also, it means that this is equal to this. When you cross multiply this and this, that is it. Or F2 is proportional to T2, and this is proportional to this. That is all. Let's do the last one. Are you done writing? Are you done writing?
Yes, sir.
Now, okay, let me see if I can erase now. Now, looking at the same formula with this thing, we can also say that frequency is inversely proportional to the root of m, the mass in a string. Do you agree with that? Yeah. That frequency is inversely proportional to its mass or the square root of its mass. Hmm? Its mass or the square root of its mass. So it just means that all what we've been saying, it just means that the first one we said that it is inversely proportional to the length. That means if the length is too long, the frequency will reduce. Now, when we look at the tension, that means if we increase the tension, we increase the frequency. Or that means in the other case, we increase the number of vibrations. You get it? Now, when we increase the mass, the number of vibration will decrease, or its frequency will decrease. Because when the thing is heavy and you want the vibration, you won't be able to vibrate as this unless it is very small. So when the mass is high, then that means the frequency will be low. You get what I'm trying to say? So if you have a guitar, that is why the guitar strings are very thin, and the guitar strings are very thin. So look at the guitar strings. There are 6 strings. You realize that the down one is the lightest, and that one when you hit it, it sounds very high because of the thickness of what you call it, or the mass of the mass and the length of that what you call it, that last string. That is it. So as you go higher, you realize that it increases. The heaviness of the music increases, or the pitch of the music increases. That the sound become very deep. So you realize that the first string, that the top string is very heavy because the mass is higher. Let me just see if I can demonstrate it to you. I have a guitar here. If you can see me. Can you see me? Can you see me? So look at this. Can you see? Can you see?
Yes, sir.
Now there's a there are one, two, three, four, five, six. I realize that the first string is very light. The first string very light as compared to this one. And you realize that the sounds are different. You realize that the sounds are different. Can you see? Now this one is also a little bit heavier than this one. The mass of this is a little bit more than this one. And this is also different. You realize that they all change. The last one with the bass is the what do you call it? The is the heaviest, or the mass of it is very big as compared to the rest. It has a huge mass than the rest. And you realize that the rate at which this vibrates is different from the rate at which this vibrates. You get it? So this just explains everything I'm giving you. That what do you call it? The vibration is the frequency is inversely proportional to the mass. So if the mass is very small, the frequency will increase. You realize that when you strike the little one, it's the rate at which it vibrates is more than the bigger one. So basically that is it, and that also brings about the changing their tones and so on and so forth. So that is it. That's why I just wanted to illustrate. So this will be like the first one. So it's inversely proportional. So if you have frequency 1 all over frequency 2, F2, that will be equal to M2 all over root M1. I'm going to get something like that. So these are known as the laws of vibration of stretched strings. So they are all what I've said. They are just known as the laws of vibration of stretched strings. So the first one is saying that the frequency is inversely proportional to the length of the stretched string. So the frequency of a stretched string is inversely proportional to its length. The second one is saying that the frequency of the vibration string is directly proportional to the square root of the tension in the string. And the last one, we are saying that the frequency of the string is inversely proportional to the square root of its mass per unit length. So basically, that's what we've learned. Now, when we have the first overtone, this is the fundamental overtone. This one is the fundamental overtone. Now, when we have the first overtone, we are going to get something like this. That means the second overtone, we are going to consider this one. We are going to consider the whole of this. So we are going to get something like this. That will be the first overtone. So in this case, the length here will be equal to this. Have you seen it? So this will be the first. This we call it the first. So this is the fundamental overtone. This is the first overtone. Then the second overtone. With the second overtone, we are going to add another one to this. So with the second overtone, here will be N, and here will be N. So with the second overtone, we have 3 N's and 2 A's. So here will be A, here will be A. And L is equal to this, one wavelength. Then the last one, we are going to get the second overtone. Then you can do it, and so on and so forth. The second overtone, we are going to get something like this. We are going to get something like this. Let me just. So I'm going to get something like this. Just add Add 1 to it. So the second overtone we have this, only this is half of a wavelength. Then from here to here is 1 wavelength. So all will become 3 all over 2. So the length in this case is equal to this. Do you get it? Hmm? Hello, do you get it?
Yes.
Good. So, but you know, for a stretch string, your frequency is equal to, you know what your frequency? Your frequency is equal to 1 all over 2L. See, all over M. That is it. Now let's do vibration in pipes. So there's vibration and what they call it, stretch strings. Let's do vibration in pipes. Can we do that one in open pipes? Then I think we are done. Oh, yeah, done. Let me clean it. Oh. Oh, yeah, Dan, you let me know. Yeah.
So please calm down.
Okay. Michelle, I wanted us to study you. I mean, since morning, I mean, what's happening is you've not been online. Why? Where have you been? So now let's do vibration in pipes. Let's do vibration in pipes. Now we are first going to consider vibration in closed pipes. Vibration in closed pipes. Vibration in closed pipes. Vibration in closed pipe. Now a closed pipe is one which is closed at one end. When air is blown into the pipe from the open end, a stationary wave is set up. So the stationary wave has a node at the closed end and an antinode at the open end. So that's how the closed pipe in this case will be. A closed pipe is one which is closed at one end. When air is blown, like if you have a trumpet, you know we are talking about air here. So when a closed pipe is, when air is blown into the pipe from the open end, a stationary wave is set up. A stationary wave is set up. Now the stationary wave has a node at the closed end and an antinode at the open end. So in this case, you are going to get something like this. You're going to have something like this. So there's a first fundamental. The fundamental distance vibration. So this one side is closed. You can see one side is closed. So here becomes a node. Then the other side is open. So the other side is open. So in that case, we are going to have, if you have the diagram, if you have this, it will be something like this. In this case, this will just be half of it. This will just be half of it. Looking at this, it will just be half of it. So it will be something like this. Do you get the diagram? So this will be something like this. When you have something like this, from here to here, and from here to here is 1/4 of what you call it, because the whole of this is 1 second. So half of 1 second will be 1/4. So the wavelength, the length will be equal to 1/4 of the wavelength. Please, are you getting it? And here will be the open space will be the anode, the antinode. Sorry. Please, do you get it? Do you get the mathematics here? Now, so we know that the length is equal to this. So length is equal to 1 all over 4. If you understand this, it's very simple. 1 all over 4. 1 all over 4. But if you want to make this a subject, you are going to get, just as we did, you are going to get this is equal to 4L. So that's what we are going to get. But we know that already. We know that the velocity or the speed will be equal to V F this thing. So we can substitute this one here. So V is equal to, the V will be equal to 4L 4LF. Now, where F is the fundamental frequency, so here the F will be the fundamental frequency. Now, with the fundamental frequency, we can also decide to make it F naught so that we don't confuse ourselves. So that when we are doing the first overtone and the second overtone, we can do it F1 or something. So let's say the fundamental frequency in the closed pipe, we can do it F naught. So what we are going to do is our V will be equal to 4L F naught. What F naught is our fundamental frequency. That's the first frequency. So the base frequency. So what we are going to do is, if you want to make F naught the subject, you are going to get F naught is equal to V all over 4L. Do you get it? And that's the lowest frequency obtainable from the instrument. So there's the lowest frequency the instrument can get. The lowest frequency. So if it was to be the guitar, you see that the bass, the lowest frequency. So that's the lowest frequency. Now the stationary wave of a higher pitch. So when we want to increase it, get a higher pitch, then we are going to the first overtone. When we want to increase it again, then we are going to the second overtone. And we can be doing it and so on and so forth, the third overtone, fourth overtone, fifth overtone, and so on and so forth. You can just be working on it. So we can say there's a fundamental overtone. Now let's look out for the first overtone. So let me just write it. So there's a fundamental. There's a fundamental, what do you call it? Frequency. Now let's look out for the first overtone. So we can look out for the first overtone. The first overtone. I'm talking about the first overtone. Now with the first overtone, that will be an upgrade. So the first overtone is like this. It will be something like this. So no. So that is the first overtone. Can I claim the fundamental frequency? Can I claim the fundamental? So we can name the first overtone to be F1. Can I claim it? Listen, can I claim it? So that's the first overtone will be the whole of this plus the open distance. So that one we are going to get node here, another node here, and we are going to get open here, which is antinode. So there's fixed, open, or free boundary. So that is it. Now, so you bear with me that the whole of this is this all over 2, you know, and this one is this all over 4. Please, do you agree? So when we add the 2, what are you going to get? We are going to get the length here to be equal to 3 all over 4 wavelength. Please, do you get it? They're all doing it together. Mm, I get it. So, uh, that is it. So that will be the first overtone. You are going to get something like that. Now, if you want to make this a subject, if you want to make this a subject, you are going to get this is equal to 4L all over 3. I getting it. So that will be the frequency. So 4L all over 3. Now, for the first overtone, we make F1 F to be equal to F1. So that it doesn't coincide with this one. So I'm going to get V is equal to, that's the frequency of the first overtone. So V1 lambda, but lambda is equal to this. So you come and put it here. This is normal mass you are doing. So V is equal to V will be equal to F1 4L all over 3. Please, do you get it? Now, if you want to make F1 a subject, that's the frequency of the distance, the first overtone. The frequency will be equal to 3 into bracket V all over 4L. V all over 4L. But you know that V all over 4L is also equal to the first fundamental frequency. So you can, this also means that the first overtone is equal to 3 times, is equal to 3 times the fundamental listen frequency. Have you seen it? Have you seen it?
Yes, sir.
Good. Now let's do the F2. The F2 will be the second overtone. So the second overtone, can I please clean the board?
Yes, sir.
Are you writing, or I can, have you written it? I can clean the board. Or you are yet to write?
I've written it.
Good. Now let's do the second overtone, and we can get third, fourth, so on and so forth. It's an instrument. So let's see. The next one will be something like this. So well, if we have this, the second one will be equal to so that will be something like this. We are going to get node, 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 then antinode. So that is it. So that will be when you do the calculation, you are going to get L is equal to 5. L is equal to 5 all over 4. I hope you know why. This will be this. This all over 2. This all over 2. And this one will be this all over 4. So you can just do the mathematics. So that is it. And you can come and put that into this equation, the first equation. But when it's equal to, here we are going to make it, because the second one, we are going to make it F2. So F2, this. Now, but you know that this is equal to 4L all over 5. 4L all over 5. 4L all over 5. So now when we have this, we can come and put this one here. So we are going to get when is equal to, I hope you are appreciating it now. F2 4L all over 5. Now you can make F2 the subject. So F2 will be equal to, F2 will be equal to 5 into brackets then L over 4L, then L over 4L. But then L over 4 is F naught, so F2 is also equal to F naught. So right from this thing, we can see that they all have a difference of 2, 2, 2. So the first F naught, then F1 is giving us 3 F naught, F2 is giving us 5 F naught. So the probability of F3 will come and give us 7 F naught. Then you increase it by 2, 9 F naught. F5 will give us 9 F naught. F4 will give us 9 F naught, and so on and so forth. And so that is it. And when you have the series of these frequencies, what we call the harmonics, the series of it. So it can be deduced that a closed pipe emits a fundamental note F accompanied by notes of higher frequencies. And so this will be the notes of higher frequencies. And so there's the first fundamental note, we have F is equal to this. Then the F1 will give us 3. So when we want to write the series, we can write F1 as the first overtone, or the first frequency will be equal to F1 F naught. Then we can write F2 equal to F2 is equal to F naught F 5 F naught. You can continue and come and write F3 is equal to F3 is equal to, looking at this, F3 becomes 7 F naught, and so on and so forth. And so you realize that it is the multiple integral. I was reading something, but so so the overtone, which has a frequency, which is an integral multiple of the frequency of the fundamental mode of vibration, is called the harmonic. So realize that this one is an integral multiple of this. The rest of the series are integral multiple of this. So the first, this thing is 3 times the F naught. Then so we can, this one is F naught. I'm coming. Then the F2 will be 5 times F naught. F3 will be equal to 7 times, and so on and so forth. So it's the integral multiple of what they call it, the fundamental mode of vibration is what we call the harmonic. So the harmonic, the first harmonic is the fundamental note. You talk to me, Ruben. Talk.
So what do you mean by integral?
Integral, like multiplied by an integer. Let me put it that way. Multiplied by an integer. So realize that this one is by 3. This 3 times the fundamental note is 3 times the first overtone is 3 times the fundamental note. The F2, the second overtone is 5 times the, what do you call it, the fundamental mode of vibration, which is the F naught. Then the F3 will become 7 times that of this one. Now when you do it, F4 become 9 times F naught, and so on and so forth. So it is the integral multiple, or the integral multiple of the frequency of the fundamental mode of vibration. And that series of it is what we call the harmonics. So the first harmonic is the fundamental note. The second harmonic is this one, F1. The third and the rest. The third is F2, and so on and so forth. So basically, that's what I wanted to explain. So anytime you hear harmonic, you can just relate to it. The harmonic is the integral multiple of a frequency of fundamental mode of vibration. So basically, that is it. I hope you get it now. So integral, twice of U, 3 times of U, 5 times of U is an integral. So that is it. Please, you get it now.
Listen.
Good. Now let me erase it and let's do the closed open pipes. Let me erase and let's do open pipes. We are done with closed pipes. We're done with stretch strings. Let's do the open pipes. Can I clean it?
Is it so?
Is it? I'm waiting. No worry.
Silicon Valley. Which agency is responsible for providing information on the weather and climate conditions of an area? Which agency is responsible for providing information on the weather and climate conditions of an area? Yes, it is. I could see Nana trying to push you to do this.
Wow.
Well, you are correct. And congratulations. Moving on to happy kids. In the solar system, the fifth planet from the sun is known as Silicon Valley. Describe the process that takes place during fertilization in animals. Describe the process that takes
Some done.
fertilization in animals.
So let's do that of a close open pipe. Open pipes. So we've done the closed pipes, we are doing the open pipes. So with the open pipe, the first thing I'm going in a pipe which is open at both ends, there are antinodes at both ends, and therefore the length of the pipe is half of the wavelength when the fundamental is produced. So when you say when the fundamental is produced, when the first distant frequency is distant produced, or the first vibration is produced, that's kind of that's what we did. So we can just consider the first with an open. It has two sides, two of the sides being open. So I'll have something like this.
So we're going to provide you with some sheets of paper so you can get your scribbling and your answering going.
Let's draw it well, yeah.
A few questions here for the students, and you're going to be answering them. I hope you guys are ready for the mathematics. Yes, they've drawn out their pens and are ready to scribble away, and so we're going to have them in just a bit. Now, how's the competition going so far? Are you enjoying yourselves? Yes, you better be. Who do you think is going to win? Are you sure?
So that's it. So it has one node, and then because it's opened, it has two antinodes. So here's antinode. But looking at this, you just bear with me that the length here will be equal to this all over 4. This one to this all over 4. So when you add it, you are going to get L is equal to the length of both. That's it. We are doing the fundamental. That will be equal to this all over 2. When you add both of them, then we can use our normal mass. But this will be equal to 2L. This will be equal to 2L. So you can come and put it into V is equal to the speed of the wave is equal to this all over. So when you come and factor this one, you're going to get V is equal to 2LF. So we can make F the subject. You can also name it F naught. So that'll be P all over 2L. Have you seen it? So that can be our first. These are fundamental notes. Now we can check our first overtone. So these are fundamental mode of vibration. Fundamental mode of vibration. Then we can talk about the first overtone. The first overtone, RST. First overtone. The first overtone. That will be something like this, yes. That will. That's two sides open. So that is it. You can decide to draw a line to touch it or something. That will make it very nice. So So it will be something like this.
More seconds to try it out. So time is up, unfortunately.
So when you have something like this, you know this one will be equal to all over 2. This one will be all over 4. All over 4. So the length will be equal to this plus this plus this. What are you getting? What are you getting? 1 over 4 plus 1 over 2 plus 1 over 4. This will give you 2 over 4 plus 1 over 2. So I'm going to get this plus this will give you this. So we are going to get this to be equal to 1. So we can name the first f to be equal to f1 will be equal to v all over L. V all over L. F1 will be equal to V all over L. I'm coming. I'm coming. V, V all over L. So I'm going to get something like this. V all over L. So but this is equal to, this is not equal to this. But if you want to make this one being equal to this, when you multiply this by 2, it will cancel and be something like this. So F1 will be equal to 2 of F0. Twice of this, when you multiply this by 2, we are going to get this. We are going to get this. So we can say, but if this is F0, then that means twice of the F0 can give us F1. That's the mathematics. So that's what we just written here. That's what we just written here. So you realize that this one starts from 2. And when we do that, Ruben, talk to me. Ruben, talk.
So I don't understand how because we said F1 is equal to
V all over L.
V all over L. And
Yes.
F0 is
it's equal to V all over 2L. So if you want to relate it in terms of F0 and V F1, then that means you have to multiply this by 2 before you can be able to get, because when we multiply this by 2, 2 cancel this. Then you are going to get V all over L, which will be the same as V1. I want to relate it in terms of it being equal to twice of F0. So the F0 is this. Now the twice of this F0 will give us V all over L, because the 2 will multiply, will cancel this. Do you get it?
Yes, sir.
Good. So we can see. Now when we do for the third one, when we decide to add additional 1 of this and do for the third one, we are going to get 3 of 3 F0. We are going to get F2 is equal to 3 F0. So when you do it, then you come and get F3 is equal to 4 F0. F4, so F3 will be equal to 4 F0. 4 F0. Then F4 will be equal to 5 F0. So that is, so you realize that with a closed loop, the difference was 2, 2, 2, but this one the difference is 1, 1, 1, 1, 1. With the open loop, the difference is 1, 1, 1, 1, 1. So for an open pipe, all harmonics, odd and even, are present. So this one, you realize that they are odd and even, they are all present. The first one is 2, 2 is even, 3 is odd, 4 is even, 5 is odd. But you realize that with a closed one, they are all odd numbers. 3, 5, 7, 9. They are all odd numbers or something. Do you get it?
Yes, sir.
Good. Now finish writing and let's. We are almost done. We are done. But let's finish the level. And let's see.
Please, I'm done.
Good. Now let's consider something we call end correction. If I don't teach you, you might meet it somewhere and will be like, "Said didn't teach me," so I'll have to teach you. end correction. Let me clean it. Okay. End correction. And oh, end correction. And normal that one happens in an open pipe, or maybe a pipe with one side closed. It happens. So we normal in practice. So just listen. In practice, when air is in a pipe, when you blow air in a pipe, so when air in a pipe is vibrating, so basically, if you are using a trumpet, before the trumpet will vibrate to give the sound, you are supposed to blow air in it. I hope you know that. That's for the stretch string. You have to strum it. As for the trumpet, you have to blow air. Now, the vibration of the air is what causes the sound, and so on and so forth. Now, when air in a pipe is vibrating, a small amount of the air beyond the end of the pipe also vibrates. So we assume that there's a small amount of air beyond the pipe which also vibrates. Now, in calculation, we must replace L, the length of the pipe, with L plus C, the length of the vibrating air column. So we just assume that if in a pipe, when you blow air, the air also vibrates. A small portion of the air vibrates at the end of what they call of the tunnel or of the end of the pipe. And that one, when we are calculating, we are supposed to factor that the length of that column, the air column which was vibrating, into our calculations. So basically, that's what it means. So when you blow it in it, the air after the one in the middle and so on and so forth, we assume that at the end of the distance, there's that column of air which vibrates. And when we are calculating, we are supposed to factor it. So when we are factoring it, we just do that. That's what we call the end correction, and it is represented by C. End correction, it is represented by C. So when a question says M questions on the end something, when you're calculating, just factor it into it. So you're just going to do the theory, the mathematics around it. So for instance, when you have a closed this thing, with one side closed, when you have something like this, when you have something like this, we just believe that there's supposed to be a certain air column here. That normally we don't calculate. There's supposed to be some air column that normally we don't calculate. And that air column we name here C. We name here C, the air column. And the whole of this one is the L. The whole of this one is the L. That's the whole of what we call it, the tube or the pipe. That's it. Now you bear with me that this is all over 4. So here will be N, here will be A, So in calculating for the length, you have to add C to it. So we are going to get the length to be L plus C. And L plus C is equal to a wavelength all over 4. Basically, that's what in calculation. So in this case, when you're calculating, we factor the end correction to it. That means the vibrating, the air column, vibration air column or something. So we are going to get this is equal to, the wavelength will be equal to 4 times L plus C. 4 times L plus C. So I'm just going to factor this one to it. So now when we are putting it into F is equal to V, V is equal to F, V is equal to F lambda. We are going to get F is equal to V, V all over F is equal to V all over 4 into bracket L plus C. So that is it. When we consider the end correction in it, so that will be the first one. Now, in the case when you have two sides, both sides being open, like when you have something like this, when you have two sides being open like this, the C will be 2. So, okay, let me. So we will consider a certain C here. We will consider another C also here. Well, both sides are open. So here this will be C plus C. That will give us 2C. So here we are going to, when we consider the L, here will be L plus, the L is from here to here. So here will be L plus 2C will be equal to, this one will be lambda all over 4. This will be lambda all over 4, which is equal to lambda all over 2. So this one will be lambda all over 2. So we are going to get lambda to be equal to 2 into bracket L plus 2C. So basically, when we factor all into this one, we're going to get F is equal to then all over 2 into bracket L plus 2C. Do you get it now? So this one is for an open pipe. This for a closed pipe. That's for closed pipe. Close. When we are considering the end correction. This is for open. You get it? So this is LO, please. L plus 2C.
Yes.
So that is it. The next time we're going to solve mathematics. We are going to solve questions under it. Then we finish. Then we do the apply effect. Then we are done. Resonance and apply effect. Then we are done. So copy it and let's end. I'll just upload it right away. I won't wake up cry, otherwise I'll forget.
1 point to be awarded for each bonus question, which, of course, is answered correctly. 1 point, however, will be deducted for each bonus question which is answered wrongly. So, if the students are ready, if the members of this auditorium are ready, viewers, if you are ready, it's time for us now to have the feel and the taste of round 2.
Good.
You're welcome back.
Good. So that brings. I said, remind mommy I'm broke. Remind mommy of my balance last month. We'll talk about this month later. So remind. So that is it. I'll upload it very soon. How should I even title it? Okay, mode of vibration. So I'll send it to there. Bye bye. Take your medication so that you get better. Straight recovery. Bye.
Understand the question, over which period was former president of Ghana